This is Dr. Pratima. I'm back with you with the topic helium neon laser, which is from the first part of your module 3 of the subject waves and optics. In my previous lecture, we have seen the history of laser and how laser is different from light on behalf of its characteristics and the basic concepts of laser like spontaneous emission, stimulated emission and stimulated absorption, which happens when the atoms are subjected to external sources of energy like photons. We have also seen the basic needs for the emission of laser like population inversion and the experimental arrangement to reach this population inversion, which is the optical resonating cavity. And we have also seen what are the complete components needed for the production of laser and what is the complete action which is taking place inside the optical setup, that is the cavity, which is known as the lasing action. And we have also seen the first ever invented laser in solid state medium, which is ruby laser invented by Myman. If you want to go back to any of these concepts, you can go into the videos whose links are provided in the description box. Now, helium neon laser is a type of gas lasers. First, let us know what are gas lasers. Gas lasers are nothing but these are the lasers which have the active medium as gases. And the laser which is passing through this gas can be occurred either through single atoms or molecules. Mostly, lasers have active medium as mixtures, where one component of gas is mixed with another component of gas in some ratio. And coming to the pumping source, mostly they are used, they are electrical gas discharge, electrical discharge is used as a pumping source. Some very few gas lasers also use chemical reactions as pumping source. And when the electrical discharge is used as a pumping source in gas medium, the electron collisions in a gas discharge allow the atoms of the active medium to excite to the higher energy levels. And the problem here why you cannot use the optical pumping as you have used in the ruby laser is because the energy levels of gaseous atoms are discrete. And during the operation of the complete lasing action, the gas is often in a state of plasma, which contains gaseous molecules with charged particles in it. And many of the gas lasers, they emit very good quality, and this is because of the inherent nature of the gas optically. The distortions of gas in the optical regions are very less. And if you have to reach this, you have to concentrate on the temperature gradients. You have to consider to what sort of the optical range you want to achieve and what sort of the optical range of spectrum you have to filter off, and you have to maintain the temperature responsibly depending on your achievement. So coming to the operation of the voltage, it needs pretty high voltages and of course a high electric power also. In some gaseous lasers, they even use high power to quickly circulate the gas with forced convection and fast flow phenomenon. We are now having the helium neon laser as a topic in our curriculum. This is the first invented gas laser to overcome the deficits or the disadvantages which we have seen in ruby laser. What was the disadvantage in ruby laser? We didn't get a continuous wave-like output. We got the output in the form of pulses, of course, of a very high voltage. And with high voltages, we got pretty high output, which were useful even today to drill holes even in resistors and some electronic components and even on metal surfaces. So the only deficit there is that there is no continuity. So Ali Jawan and his co-worker William R. Bennett, they worked on gaseous lasers, like taking gases as an active medium to overcome this disadvantage. And in 1960, they were successful in inventing the first gaseous laser. The strongest laser emission along with his colleague, he was able to give at 1153 nanometer around near infrared spectrum of the light, and it was continuous and it was not pulsed. That means it was not pulsed, and it was a beam of coherent light. That was a major victory of Ali Jawan through this mixture of helium and neon as an active medium. And of course, after 6 months later, another pair of scientists in the same Bell Labs, they made a similar device of the optical cavity, and they could get the pulse of 632.8 nanometer as an output. Here on the screen you can see Ali Jawan and his co-worker William R. Bennett working on the discharge tube, which is carbon dioxide laser, which is not there in our curriculum. If you want to read about their invention, you can go through this link. Now, we know that to produce laser, we need 3 components. One is the active medium. The second one is a pump. That means what is the source you are using to excite the atoms of the active medium, and the optical resonating cavity. So now, in helium neon laser, you take the active medium in a ratio of 10:1, taking helium and neon as the gases. It doesn't mean that you take it in the form of volumes or the number of atoms, but it is the ratio of the pressures in terms of the millimeters of Hg. Suppose if you are taking 5 millimeters of Hg pressure of helium, then neon will be around 0.5 millimeters of pressure of mercury. So it means that always helium is maintained in higher number or higher quantity than neon. So this is what you will have to understand as the active medium. So now this is placed in an optical resonating cavity, which is a quartz tube, which you are able to see here, of around 80 centimeters long and 1.5 centimeters in diameter. This was maintained by Ali Jawan, whatever I'm telling the dimensions. And even the helium neon ratio was also not taken accurately, but because that was the first invention, they just took a rough mixture, which I have mentioned there. And they placed reflectors there because, as I have told you in my previous lectures, you will need to make a resonating cavity which has one side a partially reflecting surface and the another side a fully reflecting surface, and the partially reflecting surface should be towards the output of the laser. And these reflectors, they maintain that they would be most efficient in the wavelength region of 1100 to 1200 nanometer. And before going into the optical resonating cavity setup, first let us understand what is the excitation source they used to excite the gaseous atoms to the higher energy levels. You can see in the picture the discharge electrodes. Potential difference is applied of around very high voltage, around 2 to 4 kilovolts, so that it will discharge electrical energy into the gaseous active medium, which is enclosed in the discharge tube. You should remember one thing, that this tube is made up of quartz, and this quartz is maintained here for a very special reason, which you will be understanding in the coming slides. And now you are able to see the partially reflecting mirror and the fully reflecting mirror in the diagram. So these mirrors are maintained so that they will be at Brewster angle to the axis of the tube, at a certain angle which was studied by Brewster, hence you call it as a Brewster angle. So this will enhance the polarization of the light so that you will get a well polarized light in the output. And this will also minimize the loss, and it will give 100% transmission of radiation, the radiation whose electrical vector is parallel to the plane of the incidence. So this is the setup of optical resonating cavity. And the mirrors can be maintained in two ways. The mirrors can be either cemented to the tube, or sometimes, if it is very long, they can be clamped external to the tube and seal the glass windows oriented at Brewster angle. So in the picture, you are able to see that they are clamped to the mirror. That means they are attached to the, not mirror, but the discharge tube. The mirrors are attached to the discharge tube. Hope you have understood the construction of the helium neon laser and all the three components. Now, what exactly is happening in the helium neon mixture, which you have taken in the ratio of 10:1 ratio of the pressures of the millimeters of Hg. So what happens here is, once the discharge, the electrical discharge is released, helium atoms act as a source to excite the set of the atoms, whether it may be, I can say that the mixture of the atoms, to raise the energy. That means it acts as an excitation source to receive and go. Why? Because, as I have told you, these will be larger in volume. When we look into, if you have to understand in terms of volume, as I have told you, 10:1 ratio, so they will be larger when compared to neon. So they will be standing first to absorb all the energy from the electrical discharge, and they excite to the higher energy levels, which are 21s and 23s levels. So once they go to the higher energy levels, there is neon mixture, neon atoms also in the mixture. And if you look into the energy levels, there will be two energy levels in the neon, which will be similar to that of the energy levels of helium. On that behalf, I can say that these helium atoms, which have excited to the higher energy levels, will have the same energy which can be transferred to that of the neon atoms. So once the energy is transferred from the helium to the neon atoms due to the collision, because both of them are together because of the diffusion property of the gases, so the energy is transferred. And this transfer of energy is known as resonant transfer. So now they reach a metastable state on the neon side, which are 3s and 2s respectively, from 3s and 1s levels of helium. Remember here that the left side of my thing is helium and the right side levels are just neon. So there is a transfer from helium to neon, and this transfer is in terms of the energy. So now that there is the neon atoms have excited to a metastable state, and you can understand that the higher level energy, the levels of energies are populated, whereas the lower levels of energies are having nullified population. That means there is no atoms of neon in the lower energy level. Absolutely, we have reached the condition which is required for the stimulated emission of radiation, which is the population inversion. So population inversion have occurred between 3s and 3p, and 3s and 2p, and 2s and 2p. So because of this population inversion, we can see that 3.39 micrometer of wavelength of radiation will be occurring when the atoms jump from 3s to 3p. You can see here that the distance between 3s to 3p is different to 3s to 2p, and is also different from 2s to 2p. That's the reason why you get different wavelengths as outputs when the atoms are getting de-excited from 3s and 2s to 3p and 2p levels. So, and you can also see that there is a change in the lifetime. So what will happen here is the low population inversion, as it is achieved between 3s and 2p, you can get 632.8 nanometer wavelength of radiation as an output. This is a very strong energy which falls in the red color of the spectrum. And this is what is desired. And you can also see from 2s to 2p, there is 1.15 micrometer of wavelength, which is wavelength spectra, which is coming out. And these 3.39 and 1.15, these both fall under infrared, whereas this is a very strong red color. So if you have to only acquire this 0.6328 micrometer or 632.8 nanometer transition alone as an output, is it possible? Yes, it is possible. You have to just use the system, whichever you are using the system, you have to make a small change. What is the change is you have to choose the material, a glass which can absorb, that is quartz, which can absorb this infrared. So quartz can absorb this infrared spectrum. That's the reason why I have told you in the beginning, the discharge tube should be made up of quartz. Of course, in the present research, we can modify the glass properties into whatever way you want by coating it with different types of films or even doping with some other semiconductors. And now the end mirrors can also be coated with some materials like dielectrics so that they can provide reflectivity only for the desired high wavelength, that is 0.6328 micrometer transition only, and trace it out as an output and knock off all the undesired infrared wavelengths. You have one more challenge here. You need to have, what is the main challenge here is, you need continuity. This is what was the challenge for Ali Jawan, right? They started off to knock off or to overcome the disadvantages of ruby laser. In ruby laser, there was no continuity. So if you can understand here, the helium atoms have absorbed the electrical discharge and raised here and to here, and there is a transfer of energy, and they have, from here to here, they have de-excited. So after coming from here to here, they will make a fast radiative transitions to 1s level of neon. And from now, if they will have, if you need to have a continuous emission of laser, this transition between 1s and the ground state should be fast so that this neon will come down and this helium will again go up. If this has to happen, what should happen is this neon, when it comes down to the lower energy level, it will happen only through the diffusion phenomenon. Diffusion phenomenon where the neon atoms will strike the walls. That means this transition from 1s level to the ground state can be achieved only when the neon atoms can collide with the discharge tube walls. So what does that mean? You have to maintain the diameter of the tube sufficiently small such that the neon atoms can collide and they can de-excite. The neon atoms can de-excite to the lower energy level so that when the helium is transferring its energy here itself, the transfer of energy from helium to neon, once it happens, helium comes down to the lower energy level. So now this neon, once achieving its de-excitation because of the diffusion and hitting the walls and coming to the lower energy level, the energy which is coming in the form of electrical discharge again allows the helium atoms to raise to the higher energy levels, which are 2,1s and 2,3s, and the procedure continues. So you will have to understand that you will have to take care that this transition happens very fast so that there will not be any delay like pulses, like what you have seen in the ruby laser. So if you have to have a continuous wave like output of laser, you will have to make this 1s to this neon transition very fast. That should be rapidly. Suppose, can you really excite this, or can you really de-excite this, or can I say even the output? Can I increase the output, that is the efficiency, which is very less, that is 0.2%? Yes, it can be done. One thing you often come to understand is, can I use the source, that is the pump? Can I enhance the pump to enhance the efficiency, right? Because that's the only thing which we are using to excite the atoms. So we often think that that's the only source which I can use to enhance the efficiency. But what happens here is, once you enhance the discharging current through the gases, there is large probability that the 2p levels get populated. these 2p levels get populated, because once the helium has allowed its energy to pass through neon, they come down. If you increase the pump, what will happen is they will again excite, and the 2p levels, if they get filled, what will happen is the population inversion between 3s and 2p, 3s and 3p, and 2s and 2p will be ceased. That means they will be stopped. If that's stopped, again the whole phenomenon will be disturbed. So that's the reason why you should understand that the efficiency, which is very low here, that is 0.2%, cannot be enhanced by enhancing the discharging current through the tubes. But the only thing you can do is you can just take care of that a single wavelength, which is the higher wavelengths among whatever you get. You are getting three ranges of wavelength. Among that, you try to take out the best wavelength, which is 632.8 nanometer, which is coming out. So it's not so easy. You have to maintain certain experimental setup for this. So you can use as I have told you, the quartz setup. That is the quartz as the material for the discharge tube. Apart of this, you can also coat this with, as I have told you, with dielectric materials. And if it is for a small tube, this would be enough. Like coating dielectric materials on the Brewster windows will be enough. But if it is for high power, if you want to get a high powered helium neon lasers, you will have to place magnets around or a part of this particular windows or the reflecting surfaces. If you want to still get more good highly intensified red color out and knock off all the infrared outside, the still more advanced technology is you can use an infrared filter and place it in between the cavity, so that all the unwanted infrared wavelengths can be absorbed by the filter, and you get only the 632.8 nanometer wavelength as you require. This is required. Why? Because this is very coherent, and this is very coherent, and it can be used for very high applications when compared with the infrared. So with this output, you can also use for different applications like interferometric experiments, like if you want to study the structure of any material you want to prepare or you have prepared, then you can use this. And this is used mostly in your classrooms and research laboratories. And even in metrology, surveying and alignments also can be checked. And you can see this in your libraries and in your whenever you go to any supermarkets, you can see the scanning of with a machine gun-like machine on the barcodes. So that's the laser which is used to read these barcodes, and you can also use them in scanners where the optical character recognition is done by the machine. And the 3D photography, which is known as holography, also falls under these applications. And to get good targeting also in guns, this is a wide range of application you can see. Why a part of these applications, what are the advantages when you compare this with the other lasers is it has good coherence. It has good coherence, and comparatively to ruby laser, if you see, it is very cost effective, and it's a very simple construction. You need not take a helical flash lamp and maintain a cooling effect. So this is comparatively very less and complex. That means very simple, and it is very safe because you're using very low power compared to the other lasers. Of course, a few of these will fall under the disadvantage because you got very less efficiency, that is low output power. And when you want to filter off the wavelength which you want to require, it's not so easy, and it is a bit cost effective, and it needs skilled person to do so. And you need high voltage because you will have to maintain the gain medium so much as such that you can get a proper output, and to seal the tube so that this ratio of the mixtures are maintained properly without any leak is also a challenge. With all these things, it is still more efficient for us to say that this is a successful first ever invented laser. Why? Because we were able to overcome the defect which we have seen in Ruby. Thus, Ali and Jawan could give the first ever continuous, highly coherent laser through helium neon mixture. Hope you have followed all my video lecture. And if you want to read more, you can go through the link which is given in the second slide, that is the introduction of the discovery of this helium neon laser. Hope I meet you in my next class where we will be discussing the applications of laser and solving a few numericals based on this module. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.